In this video, we will learn about aromaticity, which is a special case of delocalization of pi bonds. So before we talk about aromaticity, it's valuable for us to look at a type of a reaction called a hydrogenation reaction, in which a pi bond reacts with a molecule of H2 and essentially adds those two hydrogens to the molecule. This is called a reduction reaction, but for our purposes right now, all we really care about is that there is a change in enthalpy for that reaction. And for ethylene here, that change is negative 32.8 kilocalories per mole. And this sets up a benchmark for us to compare against other pi bond containing molecules. So people have measured tons and tons of heats of hydrogenation, and from those measurements, some interesting observations were made. And so these three observations are that, first off, we can show experimentally through these heats of hydrogenation that conjugation of pi bonds is stabilizing of those pi electrons. Secondly, there are some anomalies where the conjugation is extraordinarily stabilizing. And then finally, there's some more anomalies where actually conjugation is destabilizing. And so let's look at examples of these. So I'm going to pull up a series of molecules here. So this is pentene, 1-pentene, 1,4-pentadiene, and then 1,3-pentadiene. And what I'm trying to show here is we can kind of compare if we have just an isolated double bond, two isolated double bonds, or two double bonds that are conjugated together, and see how that affects the heat of hydrogenation. So if I go ahead and pull that across, so if I just look at 1-pentene, I get a heat of hydrogenation of negative 30.1 kilocalories per mole. And if I were to go ahead and predict for these, I would say, well, if one of these is going to give us this delta H of the reaction, then two of them should give us twice that, right? And so if I go through and predict, then it might be logical to predict those values in gray for the heats of hydrogenation for these two molecules, right? Exactly twice. You go and run these reactions and measure these change in enthalpies, and you find that, yes, for 1,4-pentadiene, you get approximately what you predict. But you go and run this hydrogenation for the conjugated double bonds, and you end up measuring a value that's quite a bit less negative. So not as much of a change in enthalpy overall. And so that was kind of experimentally a first indicator that something is going on when pi bonds are nearby to each other. And it was the first experimental proof of conjugation being stabilizing. If it's a little bit weird to understand kind of how exactly this means that conjugation is stabilizing, let me pull up an energy level diagram to help us understand this idea. So what I'm showing here are kind of some relative energies. I'm showing you the molecules, some of the molecules that we are looking at, and then in all of the three molecules here, once we add a bunch of H2 and hydrogenate them, we will always end up at the same place. So this kind of sets up a relative comparison from which we can extract information. So again, we would expect this energy gap right here to be referring to the change in enthalpy of the heat, or the heat of hydrogenation of negative 30.1. So that's that gap right there. And we would predict that another 30.1 kilocalories per mole up gets us to the diene like this. And since we have this conjugated system I'm showing in blue here, that is overall less heat of hydrogenation. So that means it's not quite as high in energy as the pentadiene here, the 1,4-pentadiene. And so what that means is that the overall heat of hydrogenation is going to be a smaller amount, but that's because this is inherently starting off at a more stable state, right, relative to the unconjugated version. So that's why this lower number tells us that there is stabilization. So let's look at the observation 2 here, and which states that some conjugation is extra stabilizing. And so the series that we'll look at is this series of 6-membered rings. So we have cyclohexene, cyclohexadiene, and then benzene. So we're going to go from one double bond to two conjugated together to three conjugated together. Again, same idea, we'll look at the initial value of cyclohexene to set a benchmark. So it turns out that for this one, you get negative 28.6 kilocalories per mole to hydrogenate. And so based on those values, we should then predict that if we were dealing with no conjugation, we would just go ahead and double the number here and then triple that number to get to this predicted value. So what people find is that, as we now know from point 1, you get a little bit of stabilization from that conjugation. And so you might expect that to continue, right? You might expect to see benzene might also be stabilized, and so we should get something like negative 77 or something kilocalories per mole here. That's not the case, and what we see is that benzene is extraordinarily more stable. So it actually has a heat of hydrogenation that is even lower than a molecule that has less pi bonds than it. And so this again is pointing to the fact that there is this extraordinary and extra amount of stabilization. And finally, I want to show you the situation where there is a destabilizing effect. And so we'll look at an 8-membered ring situation here. So on the left there is cyclooctene, and then this is cyclooctatetraene. And so same idea, cyclooctene has some heat of hydrogenation, negative 23.0 kilocalories per mole. So you would predict that you have a negative 92 kilocalories per mole from 4 times negative 23 here. But what we find experimentally is that you get an even more negative value, which indicates that this molecule is starting off even less stable than you predict. Right? And so this is again a special case where this conjugation is destabilizing. And so let's go through the definitions for these situations. Aromaticity refers to the extra stabilization that is observed in cyclic conjugated pi systems. So the thing with benzene that we see is that the pi bonds, are not just conjugated linearly, but they go all the way around in the benzene ring. And then on the other hand, we also observe there's anti-aromaticity, and that is the case when there's extra destabilization in a cyclic conjugated pi system. And so because aromaticity seems to make pi bonds significantly more stable, it is important for us to be able to identify when there is aromaticity, because a carbon-carbon double bond that is part of an aromatic system will behave very differently from a carbon-carbon double bond that is not part of an aromatic system. And so the way people identify aromaticity is using what's called Huckel's rule. An important prerequisite to Huckel's rule is that the pi system has to be completely planar or essentially planar, and of course that the pi bonds have to be conjugated all the way around in a cyclic way. And so here is Huckel's rule. If you look at a cyclic planar pi system and you count up the total number of pi electrons that are involved in that conjugation, if the total number of pi electrons fits a 4n plus 2 situation, for a situation where n is an integer, then it is an aromatic pi system. If the number of pi electrons matches a 4n situation, then it would be an anti-aromatic pi system. I think this definition is a little weird. It's easy to assume the n here refers to the number of atoms or number of pi bonds or something like that. This n has no connection to physical reality. It's essentially a quantization factor, so similar to quantization of energy that you've learned in the past in general chemistry. Probably most helpful to look at some examples here. So we'll start with benzene. So if I'm looking at benzene here, I should see that this is a 6 pi electron system because there are 3 pi bonds in the cyclic ring, and each pi bond has 2 electrons, total 6 pi electrons. 6 fits in with the 4n plus 2 if n happen to be 1, right? And so anything with 6 pi electrons is going to be aromatic if it's planar and cyclic. Now I can look at the next molecule here, and it looks like I have 4 pi electrons, 2 pi bonds here, but we have to be really careful. These pi bonds are not conjugated in a cyclic way. They're part of a ring as a molecule in the molecule, but the outer ends of the pi bond are not conjugated with each other. This is not a cyclic system, so I would call this non-aromatic. Right? It doesn't fall into either aromatic or anti-aromatic. Here now we kind of have a 1, 2, 3, 4 pi bond system. If we go all the way around both of these rings, that means there are 8 pi electrons. if it's 8, that falls under the 4n category where n equals 2. So that would make this molecule anti-aromatic. And indeed, it is very anti-aromatic and extraordinarily unstable. This one right here is a slightly different case that is worth bringing up. So you might look at this and say that there's only one pi bond and count just one pair of electrons here. But we have to be a little bit careful because this negative charge is bringing with it a pair of electrons. And if you remember the resonance pattern of 3-atom delocalization, you can have the localization with this pi bond in this direction, and with this formal positive charge you can also have delocalization of this pi bond in this direction. And then finally you can also have delocalization of this pair of electrons into this positive charge region right here. And so basically this drawing makes you think that it's not a cyclic conjugated system, but it actually is. And so here we have a total of 4 pi electrons, and thus we are anti-aromatic. All right, last one here on the right. This is cyclooctatetraene. We know that's anti-aromatic from the previous slide, but again, this is an 8-electron system, and that's anti-aromatic. So an important caveat to the idea of anti-aromaticity is that, if anti-aromaticity is destabilizing, you immediately should ask yourself, well, why would a molecule want to conjugate its double bonds then if that is so destabilizing? And well, the answer is that they don't want to conjugate the pi bonds together because that is destabilizing. And so when a molecule can kind of twist its shape to avoid being planar and thus avoid having a completely cyclic and conjugated pi system, then it can kind of avoid some of the anti-aromaticity. And so I'm going to pull up an example here to show you what that looks like. So this is a molecule of cyclooctatetraene. This is the actual structure that was determined by chemists. And so they used what's called X-ray crystallography to really kind of see into how the atoms are arranged in space. And so this is the structure. What we kind of see is that from this point of view right here, we have that octagon or 8-membered ring. But if I again tilt it back here, what you see is that it's really distorted out of planarity. Right? This is not a flat molecule at all. And the reason for this is that if it were to be totally flat, it would be really anti-aromatic and really unstable. And so because it can deform a little bit, it does deform a little bit, and this is kind of the compromise the molecule reaches. We can actually see the anti-aromaticity a little bit in the pi bonds. So this is the lowest pi molecular orbital in the molecule cyclooctatetraene, and it's actually also the highest occupied molecular orbital. So the pair of electrons in here is the highest energy pair of electrons in the entire molecule. And so if you're looking at this, I can kind of twist it around here, and what you can kind of see is that there are essentially these isolated looking sets of interacting carbon 2p orbitals, and these are very similar to the double bonds that we would draw in our structure. Right? And so this is kind of a way of showing you that the molecule is twisting away so that the angle here is not correct for overlap, and that avoids all this anti-aromaticity. Clearly, based on the experimental data, there is still some anti-aromaticity, otherwise it wouldn't be so destabilized, but it's a lot less than it would be if this was fully planar. One last thing that we had done with other conjugated pi systems before, when talking about delocalization, that we want to be able to do with aromatic systems is to draw energy level diagrams. And since these are not linear, you can't just use the kind of approach that was used before of stacking up pi molecular orbitals all on top of each other. The way to do a cyclic pi system and to do its energy level diagram is to draw what's called a frost circle energy level diagram. It's called a frost circle energy level diagram because there's sort of a circle drawn, but you actually don't really need the circle. It's just the name that has been passed on now. So the steps go like this. So first, you essentially inscribe a polygon that has the same number of sides as your molecule's ring does, and you inscribe it in a circle, and you place a vertex kind of down in that circle. Next, it works out really nicely that each vertex of that polygon will be one of the pi molecular orbitals. And just as a piece of context here, halfway up the polygon, that is the energy of an isolated carbon 2p level. So you can kind of always compare what would the energy of the atomic orbitals be before mixing and then after mixing. I think it's most helpful to see examples of this in action, so we'll do one for benzene. So for step 1 here, the idea is to do a drawing like this. Again, I have this circle and I've inscribed within it this 6-membered ring, or really a hexagon. I hope you can kind of see why you don't need the circle to draw a hexagon with its vertex down, but historically it's been called a frost circle, so we still draw circles. Right. So for step 2 then, we put in our pi molecular orbitals like this, and these would be pi 1. Pi 2 and pi 3 are arbitrarily labeled because they are degenerate in energy. Same thing with pi 4 and pi 5. And then finally we have this higher level pi 6. The pattern that you should be used to seeing now is that these bottom 3 pi molecular orbitals are bonding in nature and these higher 3 are anti-bonding in nature. Now we can go through and fill in our electrons. We have 6 pi electrons in benzene. 1, 2, 3, 4, 5, 6. And there you go. So what you're looking now at is what the Huckel theory would get you for benzene's pi system. So this pi 1 molecular orbital is really a major source of that extra stabilization of aromaticity. I'm going to pull up the structures of these so you can kind of see what this looks like. So here is that really stabilized pi MO1. Looks like a donut. This really lets you see how all of the p orbitals from these carbons are kind of all phased the same way, so that they're all interacting all the way around in a cyclic way. Just to show you the other pi molecular orbitals, this is one, either pi 2 or pi 3, whichever one you want to call it. And here's pi 3. So just even looking at this, you should appreciate that the volume and the shape doesn't mean anything when it comes to the energy. It just so happens that these two orbitals are the same in energy. Let's look at one more example. So we'll look at this molecule. This is cyclobutadiene. And if you look at cyclobutadiene, you would draw your frost circle like this, with a square with a vertex down. You can fill in your molecular orbitals like so. And if you look at cyclobutadiene, that's 4 pi electrons. That should tell you right away that's a 4n cyclic pi system, which means it's anti-aromatic. And if I fill in those 4 pi electrons, I would do it like this, right? So the fact that we have the 2 electrons having to be placed into these 2 pi MOs forces them to be unpaired. So that's a level of instability. And then secondly, the nature of the 4-membered ring, or the square here, makes it so that the center line here is the same energy as the carbon 2p orbital before it mixes with anything. So what we've really done is we've taken electrons that were at an energy in a carbon 2p orbital, and we haven't changed anything about the energy of that orbital, right? So we didn't really change the energy of that electron. And if anything, we've kind of sacrificed energy by unpairing the electrons here. And if you think back to maybe what you've learned about free radicals, this is a fairly unstable situation. This is a very reactive molecule, cyclobutadiene. It's actually not really possible to find cyclobutadiene like this drawn as a perfect square to avoid being anti-aromatic. The true structure of cyclobutadiene looks more like this, where it really stretches out two of the single bonds to avoid putting these 2 pi bonds too close to each other to avoid anti-aromaticity. So in this video, we learned a little bit about aromaticity and how to determine aromaticity. And so the skills you want to be building here are going to be the ability to look at a molecule, find whether or not it has a cyclic pi system, determine whether it's aromatic, anti-aromatic, or non-aromatic.